thanks everyone for coming to this discussion tonight. We have three very interesting scientists from the Lawrence Berkeley Lab, each with different expertise. I'm going to introduce them briefly, but I think you'll see as the sort of discussion continues, the sort of areas that they're particularly concentrated on. To my right is Bob Budnitz. He's been involved with nuclear reactor safety and radioactive waste safety for many years. He's on the scientific staff at the Lawrence Berkeley Lab. He works on nuclear power safety and security and waste management. He's held various positions in the Nuclear Regulatory Commission, wide experience in all sorts of areas of reactor design and operation. Ed Morse is on the faculty of the Department of Nuclear Engineering at UC Berkeley, and he's also a faculty scientist at the Lawrence Berkeley Lab. His particular area is measuring radiation, but he's also involved in, he's a principal investigator for the Domestic Nuclear Threat Security Project at UC Berkeley, so some interesting experience there as well. Tom McKone is involved in environmental health. He's a senior staff scientist in the Environmental Energy Technologies Division at the Lawrence Berkeley Lab. He's also an adjunct professor in the Department of Environmental Health Sciences at UC Berkeley. So a diverse set of knowledge around the issues concerning Fukushima and its effects. To start off the discussion, I think maybe it'd be interesting, Bob, could you explain, from your point of view, what exactly happened March 11th and the subsequent days at the reactors, and how do you judge those events?
Thank you. Well, I could make this 3 minutes or 30 or 300.
Let's have 3.
But I'm going to make it 3. There are 6 reactors on that site, and they were all built in the 70s. The first one came on in 1971, and by the end of that decade, there are 6 of them. They're all GE designed boiling water reactors, although the last 2 or 3 were constructed in Japan rather than by General Electric. And they've been running ever since the utilities Tokyo Electric Power. The main challenge in any nuclear power reactor, that size or any size, is that there's a large vessel filled with water. Fuel rods are inside it, and the chain reaction heats the water, and the water drives a turbine. And the main challenge is you always have to keep that fuel underwater. That's the safety challenge that every safety engineer deals with all the time. You've got to keep the fuel underwater. And the reason is that after the reactor's been running, if the water disappears from the fuel, it will quickly melt and release a whole lot of radioactivity, which at first stays in this vessel. But pressure will rise, and it'll be released from the vessel. Outside it is a very large concrete containment, but the containment could be breached too, and radioactivity would go outside. And what happened at these reactors is just that. Now, just to give you the background, there are 6 of them. Units 1, 2, and 3 were running. They were operating at the time of the earthquake and the tsunami. Units 4, 5, and 6 were not running. They not only weren't running, but the fuel was out of the reactors. There was no fuel in any of them. So they're completely safe. There was no problem with them. Their fuel was in the spent fuel pools, which are in the same building as the reactor, and I'll talk about that just briefly. So the earthquake came along. It was the largest earthquake, perhaps you know, in the last couple thousand years in Japan, although you don't really know how big they were going very far back. And when the earthquake struck, all the reactors behaved, the 3 that were running, behaved just as designed. That is, they shut down, the control rods went in, the off-site power was lost. The reactors are powered not by their own power, but from the grid. And that was lost because of the earthquake. But there's on-site power, diesel generators, and all the diesel generators started just fine. And they provided on-site power, and for the first 40 or so minutes, it was behaving just the way it's supposed to. As best we can tell, there was no damage from the earthquake, although we're not sure yet. Later, there might be some, but for that first period, there was no damage from the earthquake. They rode out the earthquake fine. But as you know, a tsunami came about 40 or however many minutes later, and it was between 35 and 40 feet high, an incredibly large tsunami, and it completely swamped the site. In particular, it knocked out the power. It knocked out the on-site diesel generator power. It knocked out both the fuel supply for all those diesel generators and also the electric distribution systems, and so they were in a situation that we call a blackout. That is, they had no electrical power. The reactors are designed to run without electrical power because they have pumps and systems that will put water back into the vessel, that the pumps run on the steam that the vessel itself is producing because the vessel's hot and it's producing steam, and some of that steam runs these systems. And they all ran fine, except that one after the other, units 1 and then 2 and then 3, those systems failed. And when they failed, quickly the reactors, all 3 of them, one after the other, got too hot. The water boiled off. There was no replacement water. The core melted, at least in our estimation, the estimation of the community that looks at this. Somewhere between 1/3 and 2/3 of the cores melted in all 3 of those reactors. The exact numbers aren't really known yet, and we're not going to know until sometime later when we get inside. So those cores melted, and a lot of that fuel slumped to the bottom. And in order to save the reactors, because they had no water to put in, the reason is that they had systems to put it in that didn't work, and they had what we call city water coming from someplace off-site. But of course, the earthquake destroyed that. And the only way to get water back into those vessels was to bring in, which they did, special pumps, and they pumped it in from the sea. Filled it with seawater, and that stabilized the situation. And it's been relatively stable ever since. That happened all in the first day or 2. And ever since then, it's been relatively stable with seawater, and now finally putting fresh water back into those vessels to replace the seawater. But in the course of all of this, the vessel didn't remain completely intact. There are valves and seals and flanges that leaked significantly, and the water went out from there into the containments and went out from the containments into the outside buildings. And also because the pressure rose, there are safety and relief valves that relieve the pressure. And non-condensable gases went out there, they're mostly noble gases, which are radioactive, and they brought with them some of the volatile iodine and cesium, and that's what's in the environment. So within certainly the 3rd day, a whole lot of stuff had escaped from those things, that the root cause of which was because they ran out of power, and those steam-driven systems failed too, and the seawater got in too late, so the cores melted, and they're still there. I'll just leave you the one of, there's a lot more to say, but I'll just leave you one other thought. We're not out of the woods yet. And what I mean by that is that there's still some possibility, because they have jury-rigged a whole lot of things out there, power and so on, and water. And jury-rigged systems don't necessarily always work reliably, especially for months, and they have to work for months or maybe even a year or 2. And so right now, the Japanese, with the assistance from a lot of other places, including us, are rigging up backup systems of those jury-rigged systems, so if they fail, there'll be something right there to pick up the load, the electrical load and the water load and so on. One last thing, it'll only take a minute to say. The 4th, 5th, and 6th units, the 4th unit in particular, the nuclear core wasn't in the reactor, it was in the spent fuel pool. And they lost cooling to that, they lost water there, and it also had a very large release, as best we can tell, from that spent fuel pool. Units 5 and 6 didn't, but unit 4 did. And so the large releases came from the 3 reactors, and the 4th one, it was that fresh core in the spent fuel pool that was its release. And now water is going back in there, and that one we hope is going to be stable also, okay? Now, just one other thing. Nobody at this stage, just to say, nobody at this stage knows whose fault this is, whatever fault means. We're not sure whether or not they were designed well but operated poorly, or there was a design flaw, or maybe the regulations weren't adequate, or there was some other, we're not sure where whatever fault there is that caused this lies, and we're not going to know for a long time. So nobody in the community I'm in is pointing any fingers at the moment. We're just everybody's working to try to keep it stable. And only later will we try to figure out, not pointing fingers to cause, to blame, but to try to figure out what we can learn that could make sure that this wouldn't happen somewhere else. But still too early to do that, okay?
Now, I'm not sure what sort of level of expertise we have in the audience, but you used, some of the descriptions you used. In the popular parlance, people talk about it's a meltdown. You said 1/3 to 2/3 of the core is melted down. What does that actually mean?
Well, the core is a ceramic, uranium ceramic, with a lot of fission products from the radioactive fission products in it, surrounded by a metallic cladding. It's zirconium cladding. And when it gets too hot, it melts. Okay? It's as simple as that. It's in a configuration at first that's okay, and then it melts. And so it's this big sort of debris bed of core material that is many, many tons at the bottom of the vessel.
Okay, and that creates a huge cleanup problem subsequently.
Yes, sir.
Okay.
Oh, it's going to be awful.
Okay, in Bob's explanation of the events, he said there were releases of radiation, and that's your field. How significant were the releases, and what do they mean?
Well, we're still learning what the releases are. If you've read the news in the last day, you'll probably hear that the Japanese government has raised this rating of this accident from a 5, which was the same as 3 Mile Island, to a 7, which is the same as Chernobyl. It's sort of surprising that they went these 2 full levels. But that's, right now they're looking at an equivalent release from the machines total from the 3 damaged reactors plus the spent fuel pool on number 4, which is about 1/10 of Chernobyl, maybe a bit less, depending on whose book you read there. So I'd like to add one thing to Bob's story, which may help a little bit. This is a genuine GE fuel rod right here. This is zirconium. This doesn't have any uranium in it today. Okay, now this material gets very hot and it reacts with water. If it gets uncovered and it gets white hot and then there's more water that splashes on it somehow, it releases hydrogen gas. If all of this material went into a chemical reaction in one of these plants, it makes the equivalent of 1/15 of a Hindenburg, which is to say about 60 tons of TNT, an equivalent explosive energy. So most of this accident was actually within the playbook that had got written back in the 1970s called WASH 1400, big government report on these reactor accidents.
Right.
But the one that took everybody by surprise was that when they started having hydrogen gas accumulate in the rooftops of these buildings, and they exploded one by one, then reactor number 4, which as Bob said was minding its own business in sort of a shutdown with the fuel and spent fuel pool, got the roof from number 3. Now, this was not on their plan. All right, and so that...
Right, who would have believed?
Yeah, this was something that was really sort of, you stand back and you have a certain lesson learned from that process. All right, and that spent fuel pool is essentially the contents of a reactor which had been dormant for a mere 3 or 4 months. I think November they defueled it. And so it's still a serious amount of radioactivity without the benefit of containment. Now, additionally, it has the roof of another building on top of it, which means you can't very well fill it with water. This was the scariest part of this whole accident from my perspective, that you had no way to actually get at this fuel. And came to the scene the Putzmeister. The Putzmeister is this enormous boom for pouring concrete. And they've managed to very, very carefully be able to inject water in that reactor. That's helped quite a bit. But there certainly were some large releases from that spent fuel pool, and you could see the white smoke billowing out as these fuel rods up there were getting very hot, covered with water, and releasing a lot of material. Now, as soon as this accident started, I suggested to some of my colleagues that we do the same thing that happened to me. I was an assistant professor here in 1979, 3 weeks before Chernobyl hit. My career has been, 3 Mile Island hit, I'm sorry. My career has been downhill ever since. And I said, well, when we had our reactor in Berkeley, we could measure air particulates on the roof from 3 Mile Island, and there was, from Chernobyl. I'm sorry, came later. We definitely see Chernobyl. We didn't see 3 Mile Island, but at that time, I said, well, with Fukushima, we might start seeing something. So some of my colleagues, Kai Vetter and Rick Norman, have been busy doing air monitoring. I think if you visited the Berkeley website, www.nuke.berkeley.edu, you'll see daily reports. And we aren't screening anything. As soon as we have what we consider competent assessment of the data, we've been posting it. You may be interested to know that at one point, March 23rd, the rainwater in Berkeley hit sort of a record of having a level of iodine in it, 131, which was approximately 5 times higher than that's allowed in drinking water by the EPA. Now that has vanished since, but we can measure all these things. It's still safe enough to the general public. In fact, we put on there how many liters of this water you'd have to drink in order to get the equivalent of a round-trip plane flight from here to Washington, D.C. And it turns out it would be something on the order of 600 liters in the worst day from that. I haven't met anyone in Berkeley that drinks rainwater, but if you do, I would avoid March 23rd bottled rainwater on that date.
It's decayed by now.
Yeah, and it's decayed by now. We've been busy measuring iodine and cesium in various foodstuffs, and occasionally found something. It hasn't been real high, but we like putting that data out there because it's my feeling that the way through this, as individuals and as a public, is total transparency. So we've been trying to give you all of the data that we have from that accident. The rough quantity that they're talking now that got released from this accident is, I think I already said this, but it's about 10 megacuries of radioactivity into the air. I suspect that will be revised downwards later, but I can't really count on it. Right. But it's likely to me that this accident will go down in history ultimately as a 6 and not a 7. And that's my personal opinion, and it's also the opinion of the government of France and various other authorities on this subject. So time will tell. As Bob said, we're early into this accident. We don't know everything, and that's what I have to say.
So when we wrote about those measurements on Echeverry Hall on Berkeley side,
yeah,
a lot of people commented and said, hang on a second, you're talking about ingesting water or locally produced milk, I think you also were measuring, and then you're comparing that to taking a plane flight. Mm-hmm. How do those two things match up? Because one is actually entering your body, the other is just you're exposing yourself to radiation. And people commented and said, isn't there greater danger in ingestion compared to exposure?
Well, you can put together a table of relative risk from doing that. It is a little bit of a problem in comparing those things precisely. It's sort of like saying how many tabs of LSD equals 1 can of malt liquor. You know, it's not a perfect science there. The point is that there is a critical organ involved with the iodine. It's your thyroid. You get a dose to that, and that causes a special type of problem that is not the same as say, the overall elevated risk of leukemia and other diseases. But there is a vague Rosetta Stone that you can have between the two, and I personally wouldn't give it any more credence than a factor of 5, but it's certainly not a factor of 1,000,000.
Okay. So, Tom, that goes directly towards your area, which, you know, what does this mean for health? I mean, let's concentrate at first for people in Japan, maybe the 12-mile zone, maybe the sort of broader area in Japan. What do these kind of releases mean in terms of health? And then let's look at what that means across the Pacific.
Yeah, well, I think it's good to start out by talking a little bit about what's in the reactor and the significance. Okay. And Bob mentioned some of the things that come out. They're in an active core, a mature core that's been operating. There's a very large inventory of radioactivity, and there's hundreds of radionuclides in there. And so it's very interesting. People kind of say, well, why are you only worried about these? Well, the ones that we worry about are, first of all, the ones that are volatile enough to come out. And secondly, we worry about the ones that are at high inventory. And even though there are hundreds of different radionuclides, the abundance are in really a handful. And those are the ones we hear about. Iodine, well, there's the noble gases, but they come out and they're not particularly of a health concern. Iodine, which is liquid, almost a gas at room temperature, if it gets hot at all, and if the fuel elements fail in any way, you can have iodine coming out in large
And
quantities.
these are the radioactive isotopes of
The
iodine.
radioactive, well, the non-radioactive, or the low, there are several, but the one we're concerned about is iodine 131 because
Right.
of its relatively longer half-life. As the temperature gets warmer, you'll start volatilizing the cesium. Now, cesium has several hundred degree boiling point, but it gets very hot. So it comes out and it condenses immediately into very fine particles. And so this is what we hear about. People say the particles. Well, they're so small, often you don't see them because they're a volatile metal that's condensing onto particles or just condensing itself into the atmosphere. That's what comes out. If it gets even hotter, we'll start seeing strontium. And we haven't seen that. And I don't think the temperature has gotten up to that point. Right. And even hotter than that, then some of the actinides, the plutonium, will start coming out. So that's sort of the stages. In a way, this is how the nuclear engineers can label that they were seeing things from the reactor because these compounds don't exist in the environment. So let's go through these and talk about what we're concerned about. Iodine, 8-day half-life. So roughly, the rule we have is 10 half-lives is essentially gone. So that's 80 to 90 days. There won't be any left at all. Okay. But it's going down by half every 8 days. Iodine, when it's taken into your body, it's rather quickly sequestered into the thyroid. And there it's been associated with thyroid tumors, but the fatality rate of thyroid tumors is less than 1%. So you can get them, but this is not really an issue for the Japanese because they got people out and they got them potassium iodide, which for that population is probably the correct thing to do. The cesium is a different problem. Cesium has a 30-year radioactive half-life. It persists in the human body for somewhere around 70 to 100 days. So when you take it in, it'll distribute in your body. Unlike iodine, cesium is distributed fairly uniformly in soft tissues. It accumulates in muscle and some of the other soft tissues. It does not accumulate in the bone. That's strontium. But of course, we're not seeing strontium. Now, cesium, because it's fine particles, can drift in the atmosphere and also can deposit out. And that's where it's soluble, relatively soluble, so it washes out of the air with the rain. The wind patterns move it differently. That's why we're seeing hotspots. If you go to Japan, you don't see a uniform concentration of radioactivity in that 18-mile or 20 or 50-mile radius. You'll see hotspots because it goes with the wind, falls out of the atmosphere. A little bit about health concerns. I mean, one of the things that I think people don't realize that we have been, not me, right? But the community has been studying the health effects of radiation since 1895, when X-rays were first discovered. Shortly after that, somebody was holding their hand in front of X-ray beam long enough that their hand turned red. And somebody went, aha, there must be some health effects. Right. And at that time, a program was begun to set safety standards. The first standard was set 3 years after the discovery of X-rays, and it's been progressing our knowledge of radiation and how it interacts with biological systems. And the types of damage it causes have been studied now for 115 years. It's probably the most advanced and sophisticated of all of the environmental health hazards that we study. For one major reason, we can measure radioactivity. Right? These guys in the nuclear engineering can measure it at levels that are unbelievably low. We can count single atoms in a liter of water.
Right.
But we cannot measure health effects anywhere near those levels. It's impossible. The health scientists cannot really see, we can't see the health effects in the variation of background, which varies between 1 and 6 millisieverts. But over that range, we cannot actually distinguish health effects. So we know the health effects are not associated with our measurements. In fact, our measurements are about 12 orders of magnitude sensitivity, but our ability to measure health effects is only about 3 orders, in a 3-order of magnitude range. So below that, we can find radionuclides, but not associated with disease.
Okay, you mentioned that in Japan they've been distributing potassium iodide for the local population as precautionary for the radioactive iodine. I know that some people here in Berkeley and in California more broadly have said this would be a sensible precaution for somebody here. What's your reaction to that?
Generally in public health, you don't want to take an action that can cause more harm than benefit. And the levels of iodine here are so low. I mean, the analogy I think you would make is, you know, at Oakland Airport, where the jets are really loud, you should wear earmuffs to protect your ears. But you know, I can hear the jets sometimes from my house, very faint sound. But why would I put on earmuffs to protect my ears from jet engine noise?
Right.
I mean, so there are precautions you take that make sense, but they're proportional to the magnitude of the hazard. And actually, the other side of that is that there are health risks associated with potassium iodide. You know, for older people, there's a higher incidence of allergies. Some people overdose themselves. There have been many reports of people going into poison control centers because they took too much potassium iodide. If someone is pregnant, it's been associated with hypothyroidism in the child that's born, and that leads to learning disabilities. So there's some actual risks associated with taking high doses of potassium iodide. So it's something that, you know, makes sense if you're at a very high level of relative risk.
Okay, good. Have we gathered some questions? Okay, thanks. Good. So here's the first question, and I guess this is probably best addressed to Bob. The news reported that hydrogen gas caused the reactor explosions. Where did the hydrogen come from?
Ed explained it, but I'll try to explain it again. The reactor core consists of rods. He showed, they're 12 feet long, but he showed a little piece of one, of zirconium, filled with pellets of uranium. It's uranium ceramics, uranium oxide, that look like little aspirin tablets. They're a little bigger than that, and they're filled with that. And it's in a big pot of water, and that's what you boil the water and make steam, and it makes electricity in the boiling water reactor. When the water goes away, the zirconium will oxidize in the steam that's around. Zirconium plus water makes zirconium oxide and releases hydrogen.
Byproduct of hydrogen.
And the hydrogen comes off, and that, by the way, there was a big deflagration at 3 Mile Island in 1979. It didn't destroy the building, but it was a big bang, and it was because a certain amount of hydrogen accumulated in that building. In the 3 reactor buildings, there was hydrogen in all 3. 1 and 3, actually, we had a big, destroyed the building, explosion. In number 2, a panel broke off the side. You've maybe seen the picture, and there's a hole about this size in it, and the hydrogen did not accumulate. So they were lucky enough not to lose that building. Came from the oxidation.
Okay. You said earlier that we don't know what's to blame at this stage. There's still too much investigation to go on. But you described the design of these reactors, and the spent fuel was in this elevated containment, above the reactor. Where is that design in place elsewhere in the world?
Well, we have a couple of dozen reactors in the United States that are basically not identical, but they're as identical as for these purposes, they're identical, very similar. They're all designed by General Electric. And there is a comparable number of those around the world elsewhere. There are a dozen more, and maybe even 15 more in Japan besides these 6. And then they're scattered around the world in several other countries. There are probably 50 or 60 or 70 of them. I'm not quite sure what the number is elsewhere in the world besides the ones we have here.
Okay. Question from the floor. Is it ever safe to build a nuclear power plant near an earthquake fault?
Yes. Yes. It can be. What that means is that we know how to design these reactors and the equipment in them to withstand these very large earthquakes. By the way, I kind of think we would have known how to design it to withstand that tsunami. You needed a bigger tsunami wall than they had. The mark of that is that, as best we can tell, this very large earthquake as best we can tell, wasn't the cause of this accident. And certainly our reactors here in California, Diablo Canyon and San Onofre, would have survived that, the motion they had there, because they're designed for a larger motion than occurred there. And we have analysis and tests that tell us that. So yes, it's fully feasible and it's been done. If there hadn't had the tsunami, I'm convinced there wouldn't have been an accident. By the way, you never know, because of course the tsunami, the events that overtook us prevented us from knowing whether or not some subsequent failures might have caused the trouble. But 4 years ago, not quite, there was an earthquake across Honshu on the west coast of Honshu in Japan. There were 7 reactors on that site, not very different from these, similar. And they all survived it without a large accident. And in fact, none of the safety systems were damaged there, even though the motion there was about twice as big as they were designed for. So yes, I think we can do that, but boy, it takes diligent and careful engineering.
Okay.
Okay.
Somebody's questioned about the 50 people working at the plant. I think that was in the early days. I suspect there are more people there now.
Yeah.
Can we explain the exposure those workers are facing? And is it possible to put a number on their life expectancy or their risks of cancers at all?
Mm-hmm. Well, to put a number on it, you'd have to know, more about the dose level. So they did move them out. I mean, they had, there's very high radioactivity in the working environment of the plants, but there are standards that they have to comply with. And as you may have read, they did have to make adjustments to there are emergency standards. So I should point out, everyone who operates nuclear reactors follows their international guidelines put out by the International Commission for Radiological Protection. And that dates back to the 1920s. It was first established in that period. And it was established to protect workers primarily. And they study all of the information and come up with that they collect data on basic research on radiation exposures, and they form committees and they make recommendations. So they have an international standard for workers, 50 millisieverts. It's actually 20 averaged out and then 50 in a maximum year. But they also have guidelines for emergency situations where you can go higher, in particular when you're trying to protect the lives of other people. And those were engaged here. But still, there are all of the standards put out by the International Commission are below acute levels. They still set standards. So what they're trying to protect against is chronic disease, the incidence, the likelihood of getting chronic disease. So because radiation has acute effects, right, which happen immediately, and then chronic effects, which happen over a longer term. Now, the chronic effects are no different than chronic effects from other environmental agents that cause cancer, benzene or arsenic, things like that, act by similar mechanisms. And they also, when you're exposed to benzene, you increase your likelihood of getting cancer through these mechanisms of oxidative stress, DNA strand break. It's not unique to radiation. Right. So the ICRP system is designed to limit the likelihood.
ICRP stands for?
International Commission on Radiological Protection. Okay. Is to protect people from immediate harm and then minimize the likelihood that they would have any long-term disease. But there were workers who went over that standard, right? They're the ones who were in the water and got some, obviously some radiation, skin radiation burns. So that's where they quickly got them out.
But in the immediate aftermath of the tsunami, I remember sort of watching television reports and commentators saying things like, the 50 workers unquestionably risking their lives, all of that. Was that hyperbole, or was that just we didn't really know what sort of exposures were at that stage?
Well, there wasn't any damage to any of the reactor cores for a day or 2 or 3, depending on which unit you were. So certainly for the first day or 2 or 3, there was no risk at all. I mean, excuse me, no radiological risk. They were just in the control room.
Nothing outside of what they're allowed.
Right, until
they were below their...
Until the cores melted, and then it got bad.
Right. Okay.
So in the first day, there wasn't any, I mean, things were working.
Okay.
And then it really got bad.
Okay, if we could move to another question. Somebody asks, for a person living in Tokyo, would you recommend any changes in routine to minimize exposure? For example, shower less frequently, drink bottled water, avoid certain foods, stay indoors, eat uncontaminated iodine-rich foods, wear disposable poncho if it rains, go away for 10 half-lives. So outside that 12-mile exclusion zone, and I think today they just extended it to some extent. So if you're 50 miles away or 100 miles away, are there sensible precautions people should be taking, or is that just needless worry?
I think there's always the possibility that contaminated food could slip through. I would advise people to not buy food off the back of trucks or something. But the Japanese are very good. They have very rigorous standards for these things, and I think that they'll do fine. The radiation does not come out in circles. And so as time progresses, we now know there's a hot spot. It's about 30 kilometers northwest of the site. And so they will eventually probably get a kidney-shaped exclusion area to keep people out close enough in. But the levels in Tokyo are pretty low, and I don't really think that just from normal lifestyle that people will get exposed to too much.
Okay. I know all of you have given a lot of media interviews, and I think
We were asked a lot.
yeah, you're asked a lot, and I know one of you said to me before we started tonight that you had a call from somebody who was going to report from there, and other than the questions they asked that were going to go on air, they said, am I going to be safe? What's your answer to somebody
Well,
like that?
I did get a call from an ABC News guy last night, and you could tell from the tone of his voice, he wasn't talking about what he was going to say on air. He wanted to know if this was okay for him, personally, to be there. And the dose that he was worried about was in a village that was outside Fukushima, right outside the exclusion area, and he was going to be exposed to about 26 microsieverts per hour. And my advice is that members of the public shouldn't entertain doses like that. But on the other hand, I've been in fields like that, but I was running an accelerator at the time. I was earning a living doing that work. He's earning a living as a reporter. You have a different concept of risk when you're involved in an activity like that where there's some benefit. It was obviously going to be some benefit to our society if he was there reporting on what's going on and that sort of thing. But that is far from a dose that would kill him, and you could calculate some small probability, a few tenths of percent, increase over his lifetime of getting a cancer from that if he were there for a week.
Okay, so 26 microsieverts, I think you mentioned the background is 1 to 6, is that right?
In that range, right, depending upon how. I mean, actually, to carry this further, it's like, what I think people fail to understand that radiation damage is not a one-time event, it's cumulative. It really depends upon your cumulative lifetime exposure. So like when the EPA sets a standard for drinking water, that's based on the assumption that you will drink at that level for a lifetime and still not increase. So like when the water that you guys measure is above the EPA standard for a day, I mean, what you have to realize is that that's not how the standard was set. It was set on the assumption that, and it's the same way that if, it's like any environmental hazard, if a lifetime at this level is dangerous, how dangerous is one day at this level, right?
Right.
Probably not very dangerous, because you have to average it out over a whole lifetime equivalent.
Okay. You've spoken a lot about the releases of radiation to the air. Someone's sent in a question about they've heard of tens of thousands of gallons or perhaps tons of contaminated water being released into the ocean. Right. What's the risk of that? I think both locally, but this person specifically asks, is there a danger that currents will carry that contaminated water into our waters?
No.
Well, the ocean is very large and very dispersive, and actually that's going to dilute these. One thing to remember is, we're concerned mainly with cesium right now. That's what's going into the water. It's relatively water soluble. It does bioaccumulate, but it spreads out very fast into the ocean. And actually, I think the land deposition is a bigger problem because soil doesn't mix itself up and it doesn't dilute itself well. And actually, when you get cesium on the surface of the soil, it can get washed down and then stay there for much longer. So even though it's a very large amount of radioactivity, it's a very dispersive environment. It's probably a better environment to put that in than on the surface of soils or buildings or other things where it has to be.
And would the same hold true for seafood as well? Is there any risk, sea life ingesting this and having higher levels of concentrated
Well, one thing
radioactivity?
is, we'll probably be able to measure it. So people will find it. But the levels at which we measure, you'd really have to look. I mean, again, because it's such a dispersive environment, I think the levels are going to go down fairly rapidly. The fish equilibrate, so the fish don't grab onto the cesium and hold it forever. They basically reach chemical equilibrium with the ocean water levels. So if the ocean level goes down, the fish levels will follow.
Okay. Someone's asked, this is kind of take a step back about sort of the explanation. So what's the difference between radiation, radioactive contaminated water, and fallout?
Right.
Explain the difference between these concepts.
Any of us could do that, I think.
Well,
Radiation,
one of you choose.
transfer of energy through space.
Okay.
So radiation could be light. And this-
Yep.
We're sitting under
Exactly,
electromagnetic radiation right now. It's just not the ionizing variety.
Yep.
That is an important thing. Sometimes people get excited about their cell phones, trying to kill them, things like that. And we are only interested in ionizing radiation. There's virtually no data that for radiological protection you worry about anything except this very penetrating ionizing radiation that can actually cause DNA upsets in your tissue, things like that. That's radiation. Fallout means typically particulate, some size of particle, typically in the micron range or so, that can get into the upper atmosphere and go places. In the case of this accident, we peaked out in Berkeley on the 23rd of March, and that was roughly something like 6 or 7 days after the biggest releases there. And if you ever go to the NOAA website where the pilots and airmen go, you'll see that the winds aloft are published for the U.S., but there's a fairly consistent pattern going about 80 to 100 miles an hour up at about 10,000 feet above. And so that's the part that carried the bulk of the plume that we saw here in Berkeley from that. And again, how that concentrates in plants, you sometimes worry about. You can have fallout in the form of, say, iodine going on the grass. Cows can eat the grass. They tend to send more of their iodine to the milk, and then babies can drink the milk, and that goes to their thyroid. So you can basically have a baby that's consuming the equivalent of a good fraction of an acre of land in the milk that they're drinking. So you worry about those things in biology that can concentrate things when physics is doing a pretty good job of dispersing them.
Okay, thanks.
Yeah.
Now, many of the questions, we kind of designed this evening around two parts, kind of what happened and what next. And many of the questions I've received are about the what next. So let's kind of go into that. And, I suppose some of these questions are essentially, where do we go from here? And I suppose one of the fundamental questions is, has what's happened in Fukushima changed a perspective on nuclear energy going forward, both the operation of existing plants and the prospects for constructing more plants in terms of the science of it?
Well, in terms of the engineering, you said science, but I'm going to say engineering.
Sure.
It could be that we're going to learn from this several different things that should have been designed differently. And if we do, even one of them, it could be several, we're not sure yet. And if we do, the community is going to learn those lessons and make those changes. And the Nuclear Regulatory Commission in our country isn't shy about shutting a plant down if it needs it. That's happened a few times over the years, but it's not common to shut it down, although sometimes that happens, or make the fixes during outages. But we don't know yet whether There are a lot of those or only a few. Surely the backfits to existing plants are going to be done if they're necessary, but it's easier to design a new plant with those features, a plant that hasn't been built yet, than to backfit an old one. It's easy to understand that. It's easier to design a new car with a feature than to backfit an old car. So all the new reactors presumably will learn those lessons too.
And how many reactors are in operation around the world today?
In the US, I think the number's 104, but it might be plus or minus 105. There are 420 or 430 around the world. We have about a quarter of them. And right now there are 2 or 3 dozen under construction, mostly in the Far East, but not exclusively, on top of the 420 or so that are running.
Right, okay. Okay, good. In terms of the health effects, what areas, where do we need to know more? What science remains to be done to find out in this area?
In the area of radiation health, I think as I said, it's the most mature of all the health effects type studies that we've done because we can measure it so well. So we are currently at a level where we understand what happens at a population scale. We understand what happens at the cellular level. There's really good experimentation. There are researchers around the world, not just in single places, that replicate this work of measuring what radiation does in individual cells and basically how it disrupts cell function, how that's proportional to the level of intensity. So I think the only thing we could do to improve it would be to get early, what we're working on in other areas is trying to get early markers in the blood or genomic markers to see damage before disease even develops, to be able to sort people out who might be at more risk of cancer from some exposure. But a lot of that's being done, actually radiation is not ranking very high among the environmental health concerns that we're looking at. We're looking at particulate matter is very important, its relationship to cancer and heart disease, a number of chemicals, and we're looking at flame retardants. There's a whole number of chemicals that the health community is studying, trying to understand not studying populations to find an endpoint, but to find middle points on the way to that endpoint. So instead of waiting for cancer to occur, we look for the early markers. So, and again, radiation was first in this field. Some of the best, what we call biological markers of early effects were first discovered for radiation. So it's a pretty mature field in the health sciences.
Are there estimates available of, I know we saw somebody circulating a paper on the number of extra cancer deaths in Japan from this. I don't know how accurate that paper was. Is it possible to put an estimate on this?
I think it's difficult without knowing. You can't put the estimate on this without knowing what the cumulative exposure is, right? You have to know you can make some estimates of what the committed long-term exposure could be, but you'd have to know what's in the environment. Now, it's been done with Chernobyl. The World Health Organization has retrospectively gone in and looked at the measurements, looked at the population exposures, looked at global levels of transport, and made some estimates of what the health commitment is.
Okay. Well, somebody's asking a question kind of related to that, where they've said they've seen divergent data on Chernobyl, that it caused 4,000 deaths, it caused 500,000 deaths, it caused 1 million deaths. What's the real data on that?
Well, the World Health Organization that looked at this, their conclusion was that they could document on the order of 50, and somebody has updated that maybe to 70. Now, these are the documented cancer deaths and worker deaths. And most of these deaths occurred in workers. The others were the fatal thyroid nodules. But they did get, I think it was over 2,000 thyroid nodules occurred in the population.
Because they didn't stop
Right,
they kept serving the milk produced locally.
They did not move people out.
Yeah.
I mean, they stayed where they were for too many days. And that reactor, instead of whereas Fukushima is happening in slow motion, Chernobyl all at once. I mean, it exploded and caught fire. But then the World Health Organization has made an estimate for the region of a committed, this is their long-term estimate of what will happen. And that's 4,000 early fatalities from cancer, half of them in the 200,000 workers, and then the other half in the other population. Now, the other number here, what causes confusion is that other study, the WHO study also looked at the global commitment. That is, you spread the radiation out, and you calculate the 100-year, cumulative, no, infinite, you actually integrate, but it's roughly 100-year committed dose to the worldwide population, which is 600,000 person seabirds. And if you take that number and multiply it by a linear slope factor for high dose radiation, then you can come up with, I come up with about 24,000 from that WHO number. So it has a lot to do with what population you're looking at, whether you're looking at the region, Europe, the whole world. What further confuses it is that not everyone uses the ICRP, the International Commission's risk factor, and not everyone uses the US, the BEER study, the biological effects of ionizing radiation. They have an estimated factor. Someone will use, find a paper somewhere and say, oh, this person has a different slope on the risk line.
Okay. Here's a question. Might be slightly difficult to answer, but it's a sort of version of what in journalism we kind of the question we constantly ask ourselves is, why are the lying bastards lying to me? And so someone has said, particularly addressed to you, Bob, and you, Ed. I mean, we are in Berkeley after all.
I may be lying, but I'm not a bastard.
No. This is to what extent?
I don't think I am.
Do you have a birth certificate?
To what extent?
I do have a birth certificate.
To what extent? To what extent do you think your interpretation of this event's severity has been biased by the fact that your careers are tied to the survival of the nuclear energy business?
I'm not sure that my career is tied to it. I think it's fair to say that I've spent the last 30-odd years trying to figure out how to make these machines safer, and there's still more to do. So I'm just happy that, I'm sad that it happened, but I'm happy to say that there's still more to do, and the community I'm in is going to do that. I don't see that that career tie is a problem. But there's a very important thing people need to understand. These reactors are not perfectly safe. They never can be. There's no such thing as something that's perfectly safe. Those risks will always be there with these reactors, as they are with other high technology endeavors. I flew from, day before yesterday, I flew from Denver, and we got on Southwest just a week after there was a problem with Southwest. I trusted that Southwest did it right, but you don't know. And of course, we take those risks because it's part of, we were visiting a granddaughter, and we're not about to not do that on account of there's a risk. But the risks from this technology are apparently greater than we thought. This accident tells us that, that's for sure. Nobody anticipated this. Whether they're unacceptable is something the broader society is going to have to figure out. I'm not going to speculate on that. In fact, I'm not even sure we know yet. But that's for sure. And one of the sort of humbling things is that despite all the efforts to try to make these things safe, somehow these, and there were 3 of them, not just one, so it was 3 of them, and they were repeated, the same issue. Somehow these reactors got into trouble that nobody in the engineering community anticipated would happen in the way it did. So that's a humbling experience, and we're going to all have to not only eat crow, but try to figure out what to do about it. Okay.
So,
Well, I don't have a dog in this fight as much as Bob does. I teach some courses in Homeland Security and nuclear fusion. However, I'm committed to education and nuclear engineering because I've been doing it since 1979. And all I can say is that in Berkeley we have a variety of bright people, and nuclear technology encompasses the existing fission technology, plus a lot of other things like medical imaging and plasma research and things like that. So we're sort of all over the map, and so I don't feel like I'm some sort of pawn in the great game of nuclear technology myself. I'm sort of optimistic that these things will have a way of righting themselves over time. It's pretty clear to me that we don't have great alternatives to nuclear energy at the present time. You kill a lot more people with coal, even with a reactor accident like this happening every 6 months. So what can you say? Certainly we're learning a lot about it. I thought it was very touching when the engineers at Fukushima wanted to get up on the roof of buildings number 5 and 6 and started cutting holes in them while the other reactors had exploded. That was a sign that they were doing their own engineering modification on the site, and they didn't want to wait for some report on that subject to come out.
That's interesting.
That to me shows that the people that are actually mining the store are trying to learn from their mistakes and not just cover themselves and go on to the next state. Nuclear engineers are very, very committed and tough people, and you can see that extended to these workers too. These Fukushima 50 are examples. I've never met anyone that's not like them. I don't think that they're that unusual in the business. A lot of people are quite committed to doing these things as safely as they can, and they're very concerned with not injuring or radiating or otherwise members of the public, especially in communities like this. They're usually part of those communities, and they don't want to have a bad reputation. So the industry will roll forward. I think that a lot of the gleeful speculation about a nuclear renaissance and lifetime extension of these plants to age 70 and that sort of thing will probably abate for a while, but it's certainly not going to cause everyone to start an immediate moratorium on nuclear power tomorrow. We can't afford it. We'll have blackouts. There's just nothing else out there right now.
You mentioned you teach nuclear fusion. Somebody has put in a question saying, since there seems to be a problem of radioactive waste with fission and also these problems of, what's happened with the releases, what about fusion?
Send money. We need about 13 billion euros. We're building a plant in France. It's going to be great. It's going a little slow at the present time. But it does have the potential of having about 1/100,000th of the biological risk of fission. So we're working on it.
Okay. Doing my calculation, I was an undergraduate about the same time you were, and at that time there was talk about, fusion was going to be the great future, and that's a good number of years ago.
It's always 30 years off. That's all.
So it's still 30 years. Okay.
Yes.
The fusion
It was
constant.
30 years off in the
Yes.
50s.
Yeah, exactly.
Yeah, that's right.
Okay, quite a few questions. I've got a lot of questions that are sort of on the perhaps more technical aspects of some of this. Somebody sent in, there's some who are proponents of thorium U-233 reactor designs. The uranium lobby has suppressed development of such designs.
You want me to
I
comment on that?
I can't evaluate that question. So,
Well, all of our reactors run on uranium, which is mined and enriched, and is a perfectly good reactor fuel. But thorium is an element. Thorium oxide is an ore, which is all around the world too, and which can be used to make a perfectly good reactor. But it hasn't been. There's a lot of thorium out there, but it hasn't been. And part of that's historical, because those designs do in fact work. The people that own thorium mines accuse the uranium people of suppressing them, and I have no idea whether that's true. The fact is that, like a lot of technology, something gets a head start and then it just becomes the technology of choice, even if something else that might be better, or we don't even know is better, has come along. But there isn't any reason why those reactors couldn't work. On the other hand, the sort of problems that we just saw would plague them too. You've got to design a reactor that can survive a blackout. You've got to design a reactor that can survive earthquakes. You've got to design a reactor that can get flooded and continue to run. You've got to design a reactor that can that can be controlled properly and where measurements can be made to understand it. Okay. Those sorts of
Can I
fundamental.
Yeah,
add
sure,
something
absolutely.
on that? Okay, thorium, yes, does have exactly the same back end, the same fission product structure that uranium has. India is particularly interested in thorium because
They
they
got
have
a
a
lot
lot
of
of
it.
thorium and they don't
Got
have
a lot
much
of it.
uranium. I saw a flow chart that showed something like 140,000 kilograms of uranium-233 moving around in the system, and thorium breeding is what their goal was. The problem also with thorium, I mean, it's no worse than uranium, but it's no better. The other problem is it still has the same nuclear weapon diversion potential. In fact, just to prove it, we blew off a nuclear explosive made with uranium-233 a long time ago. It had a perfectly fine yield. It was out in Nevada somewhere. And so really there's no real advantage to thorium except that if you own thorium, it can serve as a fuel, nuclear fuel, at least as well as uranium. And while we're at it, let's talk about MOX, because there's been some time in the press about how there was some MOX fuel in this reactor number 3, which had a little mishap as well. Now, the MOX in there was...
You should explain MOX.
Oh, MOX means mixed oxide fuel, a mixture of uranium and plutonium, all right? So somehow that deadly plutonium is out there that's the most deadly thing on Earth. It's about 10 times more toxic than lead in your car battery, and it's about a millionth as toxic as some venom from some snakes in Brazil. So it's not the worst thing. But MOX is controversial because it involves plutonium and all of that. But again, it has no increased threat in the back end of the cycle from these fission products and the decay heat and all the engineering problems of fission systems like this. And it does have the advantage that we're sitting on an incredibly large inventory of plutonium from our walk through the 20th century with nuclear weapon development. And this will help burn down the supply of plutonium. So the real risk with plutonium is not a few micrograms of it getting up in the atmosphere, but somebody showing up on your doorstep with 5 kilograms of it in the form of a nuclear explosive. And so we like MOX. We want to see reactors go forward with MOX technology. It was not a contributory to this accident in any way.
Okay, several of the questions are about, I mean, that answers, I think, some of these questions. You know, is there a reactor design that's out there present that you would say is, this is the safest design, or is it advantages and disadvantages to different ones?
Well, there are, of course, differences, just as there would be in different aircraft or different automobiles. But if it's a very large reactor like these, or like the ones we're running, their safety risks are comparable from one to the next. They're different from one to the next because of different design features and details. But their safety risks are similar. The large improvement in safety that we're all envisioning would come if somebody could design an economical small reactor. And there's a lot of work going on just in the last few years all over the world of groups and large companies, and some of the biggest companies and also small groups designing small, so-called small modular reactors where to make 1,000 megawatts instead of one Diablo Canyon, which is, by the way, Diablo's more than 1,000, you'd have 10 100s. Mm-hmm. So there are all these small reactors, each one of which is safer for sure than the big ones. But no one has succeeded yet in designing one of those that can actually be deployed that's economical. And the reason is because of the diseconomies of scale. Right. There's a lot of work going on. So that's for sure. There isn't anybody in the community I'm in that doesn't agree that those smaller reactors have a tremendous potential for being safer. On the other hand, if you're going to have 5 of these, you've got to have 50 of those.
Right.
And when you do the arithmetic, it may not be, in the end, all that, just such a huge difference.
Okay. Somebody's sent in a very basic question. Why are spent fuel rods stored on site with reactors?
Oh, they need not be.
Okay.
Oh, well, to be fair, when the spent fuel is removed from the reactor at first, it's much too hot thermally and much too radioactive, which is hot radioactively, to be stored anywhere but underwater for a few years. Depending on how much radiation it has, it might be 2 years or 3 years or 5 years. But after that, it could be, and nowadays is, stored in what we call dry casks, which are in the air rather than underwater. And those could be anywhere. They could be transported anywhere to a central repository someplace. But at the moment, they're basically all on the same site just because that's the political accommodation. But they need not be.
Okay. what's going to be done with the reactors at Fukushima?
Well, the prediction, it's still too early to say, is that it's going to be just like what happened at 3 Mile Island. 3 Mile Island sat, this was 1979, as everybody in this room who's older than I am knows, and some of the younger ones may not. It was 1979. The core was destroyed in one of those reactors, and it was 2 or 3 years of sitting there while it decayed radioactively and also thermally until finally it was safe enough to be taken apart. And the whole thing was taken apart, decontaminated, a whole lot of radioactive stuff was removed from the metals, and it's still in storage. The core itself, the melted core, was taken apart, and it was shipped to Idaho, where it sits in a vault somewhere out west of Idaho Falls in a safe vault waiting for ultimate disposal. It was ultimately to be disposed of in the Yucca Mountain Repository in Nevada that's now politically dead, as you know. And I'm sure that's what the Japanese are going to do. It's going to be a long and expensive proposition. And part of it is because this is, unlike a 3 Mile Island, this is a much more, it looks to us like the mess is much more complicated than a 3 Mile Island. Okay?
So
3 Mile Island,
this is a 10, 15 year.
everything at 3 Mile Island stayed inside that vessel except for a little airborne stuff.
Right.
That is apparently not true here. There's a huge contamination in other buildings, not just inside the vessel, but inside the primary containment, inside the secondary, in the reactor building, in the environs. There's much more contamination on the site than at 3 Mile Island, and that's going to be a really expensive and possibly dangerous mess to clean up.
Okay.
It's going to take a long time, too.
Okay. The three of you are scientists, and we're here tonight to talk about the science of these issues as far as one can judge it. A lot of the questions I have here are kind of on the policy end of things, and I know some of them that you're not policymakers, but one that I think there's several questions relating to, and you may have views. And actually, Ed, I think you answered this to some extent in your initial remarks. Somebody asked, does the public have a fundamental right to know about releases of radiation?
Yes, sir.
Absolutely. And
Absolutely.
It's important that the members of the public that have the competence and capability to do this continue to do this. You have this problem inherent in the system of the lying bastards theory you were referring to, and that is you have a lot of competent people that work in the government or in the national laboratories of the industry that can't talk for one reason or another. And then you have people that have no idea what they're talking about, and they talk all the time. And then you have people in academia that may have some capability in this area, and they owe it to the public to explain things as best they can. That's why our graduate students are up on the roof measuring these things and reporting them. And they, again, are without blame or guilt. They would, they would like to get up to the $10 an hour level one of these days. They're not trapped by the industry in any way.
But there's a very important comment that I hope everybody here understands. As best we can tell, the Japanese have been entirely and completely forthcoming. Every measurement they have made has been made public right away, and there's no evidence of anything but that. They've been candid about the confusion that they faced when they had different measurements of the same thing by different groups. They've been candid about the confusion in their interpretations of some of the difficult measurements they've made and analyses. So they deserve commendation for their candor, which was unusually complete, as best anybody can tell, on our side of the Pacific. And I think that's of course, a wonderful mark of their culture. The opposite, of course, was the 1986 Soviet situation where they hid it.
The important word here
they just hid it.
Sure.
is reach back. That's the word that the nuclear professionals like to use. And at 3 Mile Island, you saw it when Jimmy Carter was walking through the control room 2 or 3 days after the accident. Right. That let you know the rest of the government was there too. And similarly, you can't imagine the number of midnight emails we've got back and forth, reanalyzing their water radiochemistry and all the complex things. And the IAEA is on the scene. One of my former students is the chief engineer for General Electric. Those guys are going to be ready for stress leave pretty soon because they've been working around the clock trying to support the Japanese in their effort.
So, I mean, it's interesting to me that you say the Japanese government has been very open and forthright, because certainly in
Yes.
the first week or so, I mean, I remember reading articles that the Japanese were relying on statements made by Secretary Chu for their information as opposed to the government in Japan.
I don't believe that, actually.
Okay. Okay, that's, you haven't had that
No,
impression.
I think I kind of almost have, not quite firsthand, but I just don't believe that. We didn't have very much information at first, not because they were hiding it, but because they didn't. I don't have any evidence that there's anything that they knew that, hey, didn't tell not only us, but others around the world.
Well, it was hard to get, say, water chemistry data when it was clear that the water could kill you in a few hours of exposure. They're not necessarily going to stand around there with fishing poles and look at it. But they've been an upward spiral now where they've been going in all the places. And one reporter said, well, then why didn't they discover this until yesterday? Well, that's when they turned on the lights. And they were able to go into buildings and look, and then they find things,
Well, it was,
that sort of thing.
it was just too radioactive at first.
Yeah, it was too radioactive at first, but then, for example, you may recall they found the two bodies from people that died drowned in the bottom of a turbine building, and they didn't find those until last week. Why? Well, they couldn't go in there.
Right.
And so as they learn more about this, they go in more places. We're hoping it's sort of one of these upward spirals where more and more they do things. I haven't seen any effort that anyone in this industry is not 100% diligent.
Okay. You commend the Japanese government. None of you have mentioned TEPCO, responsible for the. I mean, is there anything one can say about their response, or is that difficult to judge?
Well, on our side of the ocean, our communications have generally been from the government, not from the company. The company tells the government, and so it's hard to judge, I think, from where I sit.
Well, we have a liaison with TEPCO through my department, through a liaison in general with Japanese nuclear technology. So there has been communication.
Yeah, there has been.
But that's the engineers at TEPCO. And none of the engineers have been indicted for fraud. And there has been some history of that in the past in that company, but not the engineers.
The Tokyo Electric Power Company runs more reactors than any other company in the world, I think, except the French.
French, yeah, right.
The French are ahead of them, but
Yeah.
okay, it's a large, very large company.
Okay. Somebody, this basic question, given everything you said tonight, would you feel comfortable with having your children or grandchildren living close to a nuclear reactor?
Yep. Yep.
Living close to a coal-powered plant?
Less,
That's right.
but yes, by the way, yes, but less.
Okay. Okay, good.
Where you don't want to be is right downstream of a earth-filled dam. We have a lot of earth-filled dams that are poorly engineered that make electricity, and if you don't know that, you should. And they fail every so often.
Or behind a donkey in a third world somewhere. I mean, generally speaking, what's hard about the radiation statistics also is it's hard to part out the other lifestyle things that go along with these accidents and scenarios
hard to
like
know.
that. There's a lot of people are going to be under stress. There's been one suicide, which is directly related to this accident from a
Yes.
farmer that lived in the area there. Well, that counts.
another one.
And on the other hand, just little things like people are less likely to eat fresh vegetables. They may not want to go jogging for their 2 miles every night because they're
enough.
afraid of the air, things like that. And those things, when multiplied by several million people in society, do affect the
Yeah, they do.
statistics, and it's hard to part those out. Or if they smoke cigarettes, they might smoke more because they're under stress. And things like that are all going to be embedded in those statistics, and you may never get a straight answer for what's going on.
And just to, I mean, this is not hearsay. I mean, this is well documented in Chernobyl, that the disease burden of the anxiety and the fear and the disruption was worse than the disease burden from the radiation, because people would not eat. They got scurvy because they wouldn't eat fresh vegetables. they got depression. So, whether this is allocated to the nuclear accident
It's dumb,
or the
but it's
kind of
true.
fear that's generated by it and the way people sort of build up this fear. And it's actually in public health, the whole study of stress hormones and how they impact the body is now a very important area. I mean, they're actually as bad for your body as almost any environmental chemical we've ever seen. I mean, under stress, we flood our body with chemicals that are more dangerous than things that come in from the outside.
Okay. I mean, we just have another couple of minutes. I'm just curious, in closing, could each of you explain, we obviously can't gather this group together every time there's something in the news that happens with radiation or whatever. Where should people look, in terms of your knowledge, to understand the risks themselves? Where are reliable sources of information that you could recommend if people want to figure this out for themselves when these things happen? Is there anywhere?
Well, on the reactor side, there's a wonderful source of information from the International Atomic Energy Agency, which is a UN agency in Vienna. They have their own website. They have top flight information about this event, which is updated twice a day. And you can go to the IAEA, International Atomic Energy website, and see it. It's just wonderful. They're doing a good job, and it's straight, and it's, as best I can tell, unbiased. And they also have a wide variety of information, and by the way, 11 languages or something. Of course, we're all speaking English, about reactors and the safety and the risks and so on. On our side, the best place is the U.S. Nuclear Regulatory Commission. Mm-hmm. It's your and my government agency. Okay.
On the health side, I usually go first to the National Commission on Radiological Protection. That's our national scale representative to the international community. And what I found on their website is they list links to all kinds of other sites with basic information on radiation health, how to understand radiation. They link to sites in Japan which have real-time monitoring data that you can check into. So I found that a very useful site to go to because it links to so many other useful sites.
Fair.
Could you repeat that name?
The National Commission on Radiological Protection, I think if you Google NCRP, they should pop right up.
Yeah. And then they're in Washington or Bethesda.
Bethesda.
I'm sort of a contrarian. I would work backwards. I would start with Greenpeace. And I would
That's
go
a
from
good
there.
suggestion.
And I read that, and the Sierra Club, and all the position papers, and read them. The better written statements aren't exactly as anti-nuclear as you might expect. Go from there to Manchester, the Guardian site, and look at what they have to say. They're
It's
very open.
guardian.co.uk.
Yeah.
It's no longer in
And-
Manchester.
Okay, but wherever it is, they have a good website.
national
Go from there, and then go back to the New York Times and start sort of letting each story debunk the one before it. And
That's
you will
a
arrive at
good-
the truth by circling in. And I would never suggest to a bunch of people in Berkeley that they go right to websites run by the suits, by the lying bastards. But you may end up realizing that they really don't have the agenda, and some of them actually have the facts. And then you can form your own opinion once you've seen
that's
the
good.
entire bell curve of things that are out there.
The Union of Concerned Scientists,
There
another
you
one,
go.
very useful. I mean, they
I
really are.
look at that
They
stuff all
vet
the
their information quite well. And,
I agree.
Yeah.
I agree.
Okay.
The last one?
The Union of Concerned
The
Scientists.
Union of Concerned Scientists. It's in Cambridge, Mass. It's a group that generally has been opposing reactor development and deployment for the longest time, but their website is factual and reliable, and you can count on its being correct.
I plagiarized rather material from the lecture notes.
It's okay. I mean,
Yeah.
it's just, you know,
And
Yes.
best known for having the doomsday clock, the number,
Absolutely.
the number of minutes to midnight that humanity has. Well, I think those are incredibly helpful suggestions. I think it just remains to thank the Friends of the Lawrence Berkeley Lab for organizing this evening.
I'm pleased.
Bob, Ed, and Tom, and all of you who came out tonight to listen to the three of them.
Please a round of applause for our panelists. Thank you very much. Thank you all for coming.